Hello. I don't know how this will sound. Still didn't put a blanket up, but also there's a bunch of news stories about pearl tea. Love that stuff. I've had teas for 20 years. But there's a story saying that they're running out of tapioca and there'll be a worldwide shortage sometime soon. And so I went and picked one up, and it went down the wrong way. Well, okay, not the pearl. That's what I was thinking. Someone says, "Oh, they choke on those little tapioca balls," but no, it wasn't that. It was like the last sip of tea went down my lungs, and man, I coughed up nothing. Just been coughing, so my voice sounds a little weird to me. But if only there was some way to dry it out. Maybe like you say, drop your cell phone in water or something to get the water out. They say put it in rice. And maybe if I put some rice in my lungs, it'll soak up all the water. No, I don't know. If there's some way to clear your lungs, I don't know. Let me know. But that's not what I wanted to talk about. I have a bunch of stuff still on my list of things to talk about. This was something I just happened to read the other day, I guess. Last couple of days. I've been reading a bunch of articles and watching videos about Brachistochrone. I know I'm going to pronounce it wrong. But the idea being that if you had 2 points, like if you have a nail here and a nail here on a wall, there's lots of ways you can look at that. I even have visual arts today. You could say, well, what's the shortest distance between these 2 points, right? A straight line this way. And you say, well, what if I had a chain and I wanted to hang the chain? Then it was this long. It was like a couple inches longer than the straight line. How would it curve under gravity? And you would draw a curve that kind of looked like this, maybe. And so there's the shortest distance of gravity, and lots of other metrics that you can use to try to find out the minimum of something. And somebody had the question, 1700, sorry, I'm not very good at memorizing dates, but a long time ago, let's say 1700s, there was a challenge, like given those 2 points, what would be the fastest time possible for something working only under gravity to get from point A to I should label it even, from point A to point B. I'll call one A and call one of them B. And the idea being, I'll draw a curve even, a couple of them. There we go. And like, okay, well, given A and B, if I had a track made up, a wooden track, and I put a marble at the top, and only under gravity, which one would take the least amount of time? And that's what the Brachistochrone means, the least amount of time. It's like the problem took some people weeks, and they had the wrong solutions. And the classic thing was Isaac Newton solved it in less than 24 hours. That everybody else took months to, but I guess he still had some errors in his. But eventually they figured it out, and people afterwards found that there was a better way of solving it. I mean, I'm not going to go into the solution of it. It involves a lot of sines and cosines and multiplying, and it takes like 30 minutes to explain how to solve it. But the idea is then they came up with a variational calculus based on it. The idea being in calculus, you try to find the minimum of something. So given a curve, the minimum is where the curve stops changing, right? So, that's right, I can just draw it. Let's see. So given a curve, like a U-shaped curve, it's like, well, what's the minimum? All the minimum's down here. What's special about this spot down here? Well, if you looked at the angle, that is a zero angle versus some other angle, meaning it's not really changing. And so calculus is about finding that spot there. And then they said, well, how can we set that up to find an equation? Not just like what's the minimum spot, but what's an equation of a minimum line? And that's where they came up with this calculation of variance, yeah. But the idea of coming up with these equations. And so I've been reading a lot about it, so that's just my high-level summary of it. The question I came up with while watching it is that they said the person who came up with the first solution said it was based on Fermat's theorem that given 2 points, light will take the minimum amount of time to go from point A to point B. So not necessarily the straightest point, because the straightest one is not actually the fastest one. The fastest one is something based on a cycloid. And like I said, using a bunch of equations and everything to solve it. But they said, well, that's the light will always take the minimum amount of time to get from point A to point B. And based on that equation is how they solved it then. They said, okay, from point A to point B, we'll use this thing, and it'll come up with some equations and whatever. But it got me thinking about something. So the curve actually works out to be something like this, I think, the lower one. Because the idea is it's trying to go as fast as possible, as quickly as possible, and extend it outwards, right? Because you want to get this speed here, then that speed gets translated into, or velocity. You get the velocity here as much as possible. And that velocity will translate into lateral speed as much as possible to shorten that distance. So you want to get as much uh, velocity that increases as much as possible, and then that velocity gets curved over based on the track to turn into speed on the x coordinate. And so that's why it looks like as steep as possible, because you want to get that much of it. And then it'll keep on going, right? Because if you extend it out forward, gravity is only working downward direction in a vector, the vector field. So that's the only thing you can get. So when it's going laterally along the x direction, you're not gaining anything. But they're assuming frictionless surface, so there's no loss going that way. So that's why you want to try to get as much downward as possible. Actually, it actually goes below b. So I don't know if it shows up on there. I hold it, but it goes actually down below b and then comes back up to be the fastest because it has that big curve. But they got, like I said, based on Fermat's theorem, that the minimum amount of time from point A to point B. But the problem is the curve goes this way. Whereas when you talk about like Einstein's theory of curved space, right? And you're looking at something like on Earth, and you throw something, and let's say I'm standing here and I'm going to throw something to somebody over this way. Well, you want to throw it up this way, and it'll curve downwards. But it'll look like it's going straight because space is curved. So you're throwing in a straight line, and space is curved this way. And it's like, well, that's a different curve, though. So if this whole theory was solved based on the idea that light takes the minimum amount of time, then in a curved space, which way does the curve go? Does it go above the straight line or below the straight line? Because this is, by definition, the shortest amount of time. But then again, and like I said, based on the speed, based on light itself, it's like what light itself is based on the curve of gravity. And so within a gravity field, it seems that both of them should be true. But then again, I'm thinking, well, maybe since this is actually a straight line in curved space, that it would actually look like a line that kind of dips at the end, right? If you straighten this out and this becomes a straight line, then you would actually see a curve at the end. Within this straight line itself, it would look like this. So if you took this and straightened it out, you would end up with a dip at the end of some sort. Also, I mean, the problem was starting at velocity 0. So at point A, you just let go of a marble and it goes the minimum amount of time. But light has an initial velocity or a constant velocity, depending on the substance it's in. And so I did a search online to find about it. And there was only one person on a math forum who asked about it. And it's the only thing I could find. And the person said, well, you have another force here. This thing is pushing up against it. And that's why you're getting this curve here, like the wooden track. If you have a marble, the wooden track, whereas light doesn't have that. Therefore, light follows this geodesic in a curved space. It's like, well, that's not quite true, though, because the idea was this didn't assume any kind of track. The idea was, what's the minimum amount of time? If you wanted to draw a curve between a point and you had a vector field, it says nothing about the fact that something's pushing back against it. The original problem was a frictionless surface, so just something. What's the definition of a curve that such that the minimum amount of time given a vector field? It's like, so which one is it then? Which path does light follow? I mean, if point A to B and the lowest one to be the shortest path, then why would it take the longer curved path? Like I said, it must be a curve and then a curve underneath it and it adds up, but I really couldn't find anything about it. And so it's been bothering me ever since I read that. Well, yesterday I read it, I guess. And today I was walking around looking for a bubble tea, bringing it back to that. And I kept thinking, it's like, oh, it's got to be some sort of curve. But like I said, so if anybody knows anything about that, or if some of it sparks any interest, I'll try to put some links to some of the Brachistochrone YouTube videos I was watching. They're interesting. It was interesting about how the development in the history of differential or calculus of variations and how it differs from regular calculus. So, well, we'll see. A lot of visual arts today and a lot of me moving back and forth, but hope it comes across as just something interesting. I'm just curious about that. What would be the path of light from different observers, right? Because I'd be looking at it this way. The other thing I thought about, well, trying to think about this is like, well, I'm looking at it perpendicular to it, so therefore that's why I see the curve, whereas other people wouldn't see the curve. But if you think about it, it's like, well, I'm looking off at a distance this way, so light actually has to curve to get to me through the gravity field. So does that mean when you're seeing an object in the distance that it's actually like slightly higher than I would be because it curves up or lower based on the Brachistochrone problem? But the idea is, it's like, well, when people always talk about there's an external observer to some events, it's like, well, that observer has the same properties of as light as the other people, right? So you're looking and you see the curve. It's like, well, but somebody standing a distance away has an entirely different curve that they're viewing it on. And so does that affect the equations in some way? I've never seen anybody answer that one because I've thought about that one many times where people talk about the train and the ping pong ball and all that stuff. It's like, well, but if you calculate the fact that the observer is has some sort of system as well, but not the way they describe it. But it's you have to take into account that light's moving this way, and anyway, it's an entirely different problem. So this is just I was curious if maybe I knew anything about this, or maybe I just missed it in some of the things. But I've watched a few talks on it, and yeah, just curious which way light goes. Or I guess it follows always. Well, it's supposed to take the minimum distance, but I know under quantum theory, it takes all the paths and you take the average of it, but then the time should be based on the Brachistochrone, right? So, but anyway, I'm just rambling at this point. So, anyway, take care. Hope you have a great day and a great weekend. I'll try to film something over the weekend. Had a bunch of stuff about Ruth Montgomery that I had been thinking about lately. So, anyway, take care.